my group, which is group 8, we're going to present our assessment 2. For task 1, we were given a double integration. From this double integration, we take the boundaries and we can create the graph as shown in the figure. So how to find this intersection? First, we need to equate both of the curve equation and we obtain y equal to set 5. And this value, we substitute into any of the z equation and we will get 20, which the intersection happens at set 5 and 20. And for task B, for B, we need to evaluate the given integral after integrated it to respect to z. We obtain a function with a power or Euler's numbers with the power of another function. So in order to finish the integral, we must use U substitution as shown in the slide. And finally we will be able to obtain the final answer. Okay, for task C, we need to reverse the order of integration from initially vertically, and then we need to move horizontally, which is dy dz. Due to vertically, we have two type of curve. We hit two type of curve, so we need to integrate it separately with part 1 and part 2. So the first area limits are from 0 z and to the first curve, which we need to change from z equation to the y equation. Same thing happened to the second area as shown in the presentation. And after combining both of the area, we finally obtain the area as shown in the slide, which are the same in the previous evaluation. So for task 2, we're given the two equations. The first one is a curved equation, which is x equal to z square, and a slanted plane, which is s plus z is equal to 1. But we're not given a y equation, so we made an assumption y is from 0 to 1 in order to find the finite volume. And for B, we must project the objects from each axis and is shown as in the slide. Finally, for part C, we need to find the volume of the integral for each projection. As shown in the figure, for each projection, how to set the boundaries of to find the volume. And only at z axis, we need to separate the two integral, because to z axis, there's two with it hitting a curve and a slanted line. After finishing all of the integral, we obtain a same volume for each projection.
Next, we are going to discuss for task 3, cylindrical coordinate. And for question A, draw the diagram using mathematical application. For part A, I drew the 3D diagram by using Desmos because it helped me to visualize the shape and understand the region more clearly. The solid is bounded by the cylinder y squared plus z squared equal to 9, and the parabola x equal to 16 minus y squared minus z squared. Next, for task 3, cylindrical coordinate, draw the projection of the diagram by using the mathematical application. So, for the yellow part that is shaded, that is the part that we need to calculate later. So, the blue part that is shown in the diagram is the cylinder part, which is y squared plus z squared equal to 9, while the red part is the paraboloid, which is x equal to 16 minus y squared minus z squared. For task 3, C. Evaluate by using appropriate coordinate system. Since the projection is in a circle, cylindrical coordinate are the most suitable choices. So I converted the variable using y equal to r cos theta while z equal to r sin theta. X remain the same. When changing from Cartesian coordinate to cylindrical coordinate, the area element dy dz is changed to r dr d theta. The extra factor r comes from the Jacobian, which is required whenever we transform from rectangular coordinate to cylindrical coordinate. And from the cylinder equation, we get r equal to 3, which is the inner boundary. Then by letting x equal to 0 in the parabola equation, we obtain the r equal to 4, which is the outer boundary. Therefore, the limit of the integration for r are 3 to 4, while for theta is 0 to 2 theta. And lastly, for the x is 0 to 16 minus r squared. And after determining the limit, substitute them into the triple integral and integrate respect to x first, then r, and finally theta. After simplify the expression, we obtain the final answer, which is 343 theta over 6.
Hello, my name is Wahidanya and I will be presenting about task 4, which is triple integral spherical coordinates. So given Q is bounded by the sphere, the cone and the plane, which is y is more or equals to 0. So A is to draw the diagram using mathematical applications such as GeoGebra. So the following I've sketched in GeoGebra, and I've also sketched the bounded region. And then for B is to draw the projection of diagram using mathematical applications. So I've drawn the projection as well using GeoGebra. So this is the y and z axis, and the following is the bounded region. So this is for x and z axis, and I've also sketched the bounded region. The following is the x and y axis, and the following is the bounded region. Next, we have also done the solution. So the right hand side are the limits that we have obtained. So the rho and the psi as well as the theta. And then on the left hand side is the solution. So from the solution we have obtained the final answer, which is 188.447.